Yeah, so let's talk about what we're trying to do with cosmology. Remarkably, we have a picture of our initial conditions. That is, what the universe looked like when it was only 380,000 years old, in contrast to the 3.6 billion years age it is today. And that picture comes through us via maps like this. What you're seeing here is a map of temperature across the entire sky. So think of this as like you would map out a globe, except you're mapping out the interior, uh, what you see on the sky. But the interesting thing here is, so these are temperature fluctuations, and going from red to blue here is only a few parts in 100,000. So the key thing here is that these fluctuations are tiny. They can be easily treated, if you're trying to understand the physics of them, they can be easily treated with linear perturbation theory. And we understand what is causing, or at least the physics behind what's causing these fluctuations. And again, we make these maps in the microwave. This particular map comes from the Planck satellite flown by the European Space Agency. So that's what our initial conditions are. What does the universe look like today? Eventually I'll get this right. Today, this is the kind of picture we have of the universe. This comes from the Sloan Digital Sky Survey. So it's a survey of galaxies. Each of the little points you see there is an individual galaxy like our Milky Way. And the funny shape of this survey, you see that there's this blank area along the horizontal. That's there because we live inside a galaxy which is obscuring our view in the horizontal direction. That is, we live in a disk of material. We can only see above the disk, that's up, or below the disk, to get complete maps of galaxies. And you see that there's some interesting structure here. There are clusters of galaxies, and then there are voids, and we can map out roughly, match the size of those voids to the size of those little lumps you saw in the previous picture. But the thing here is that while on this map everything looks like a point, right, it's a lot more complicated. Each of those little points kind of looks like this, and so this is a galaxy like our Milky Way. It's a disk spiral galaxy, so there's a distribution of stars and gas, all interacting gravitationally. You'll see these pink areas you see on this image are areas of star formation, so hot young stars. You'll see these dark lanes, streaks through the galaxy. That is dust obscuring some of what we can see. And the general blue haze there is billions of stars. And the point here is that these are very complicated nonlinear objects with gas dynamics and star formation and supernova going off, a lot of very complicated physics going on, although the main physics driver is the self-gravity. That is the fact that every star feels the gravity of every other star. So the point here is that this is very different than the picture of the early universe that I talked about. Lots of nonlinear physics going on. And so what are the science questions we're trying to answer in simulating the formation of these galaxies? Well, one big problem out there is, all right, the picture I just showed you, this picture here, is all this stuff you see here is what we call ordinary matter. It's made of hydrogen, mostly hydrogen, helium, fundamentally neutrons and protons, more fundamentally quarks and leptons. And the remarkable thing is all that stuff I've just described is only 5% of the mass energy density of the universe. The rest, the other 95%, is stuff which we can detect gravitationally, but for which we have no idea what its fundamental particle nature is. It comes in two flavors. There's something that gravitates like matter. We call it dark matter. Dark meaning it neither shines nor absorbs light. Matter, we see it via its gravitational effects. Dark energy, dark means the same thing. It doesn't emit or absorb light, but it has a slightly different equation of state, that gravitates differently than matter. But whatever it is, it's not baryons, the protons, neutrons, the stuff we know about. And so we're trying to use simulations to put some kind of constraint on the nature of the dark energy, in particular, the dark matter. And there has been some success in this, in putting constraints on the dark matter. Some of the earlier cosmological simulations run in the 80s modeled the dark matter with a known particle, the neutrino, the electron, muon, and tau neutrinos are known to have mass, and simulations run with massive neutrinos actually showed that the neutrinos are too light, and the kind of structures you get out of the simulations do not match those galaxy surveys that I showed you. So that's just an example of how you can use simulations of structure formation to put constraints on the type of dark matter. And these days, there's a number of candidates which we'd like to distinguish between. There are massive neutrinos that don't interact in the normal nuclear reactions. We call them sterile neutrinos. There's a particle called, all these are hypothetical particles, by the way. They've not been seen in the lab. Axions is another hypothetical problem related to what's called the strong CP problem. It's motivated by particle physics, but it could also be the dark matter. And then there's this whole area of particle physics called supersymmetry. Perhaps there's another class of particles where every particle we know about has a supersymmetric particle. The lightest of these, the lightest supersymmetric particle, could be a candidate for the dark matter. But the point of this slide is, oops, the point of this slide is that. Sorry, is there a question? Because I'm getting in. Okay, I'm not sure what happened there.
Yes, someone was not muted. I just muted him.
Okay. That there are these candidates, and we'd like to be able to distinguish between the candidates to further understand what the dark matter and dark energy is. And so that brings us to doing the computational cosmology. And here I'm just motivating why we need large computational resources to do these kinds of simulations. That first map that I showed you of the cosmic microwave background pointed out is 1 part in 10 to the minus 10 to the 5. Galaxies, like the one I showed you, are overdense by many orders of magnitude. This happens through the gravitational collapse of those tiny fluctuations into these massive overdensities. But this collapse is a very nonlinear, very dynamic phenomenon And therefore, if you're going to make testable predictions, you're going to have to do a lot of computer simulation. So what are the challenges in doing this simulation? Well, the big challenge is, of course, the universe is big. Let me give you, I just realized that you probably aren't familiar with the jargon. So the typical distance between us and the nearest star is a parsec. That's a unit of length. It's roughly 200,000 times the distance between the Earth and the Sun. So that's a huge distance. That's 1 parsec. The typical size of a galaxy, like the one I showed you, is about 20 kiloparsecs across. And the typical distance between galaxies is a megaparsec. And to essentially get a fair sample of the universe, we need to sample out to around 100 megaparsecs or larger. If you're going to do the whole observable universe, you're talking many gigaparsecs to put everything in scale. But we need to resolve things down so we can see the structure in the galaxies. And so that's the resolution of about a kiloparsec that I have quoted there. But you have this huge dynamic range, 100 megaparsecs down to below a kiloparsec. And so any computational technique is going to have to be hierarchical and adaptable to these huge overdensities. Likewise, the timescales have a huge dynamic range. We want to simulate for the age of the entire universe, 13.6 gigayears, but we have dynamics happening below the megayear time scale. For example, stars are forming on timescales much less than a megayear. And so you need something that's adaptable in time as well. And the particular challenge for gravity is that it's a long-range force. So the force on a particular, to calculate the force, say, on a particular galaxy, you need to sum all the forces of galaxies in the entire universe. That's a little bit tricky. There's a little bit of approximations that need to be made, which I won't talk about in this talk. But the point is that gravity being long range means that your calculation is very interconnected. And in terms of parallel computing, you need to get information about gravitational forces across your processor domains. And here, just to give you a picture of how these calculations have to be done. This, actually, in the lower left is a distribution of the dark matter in a volume roughly 25 megaparsecs across. Actually, this image is very similar to one of the test data sets that I've provided for you. And so one of the features of this particular data set is we're trying to capture the gravity in a rather large volume, but we're focusing our resolution on a particular galaxy. And it's the galaxy we've zoomed in on, and you see in the lower right. This is in dark matter. The dark matter is roughly spherically distributed, but there's a lot of substructure. And the visible material, the stars and the gas that we see, is actually 1/10 the size of the entire dark matter halo. And you see I've zoomed that in to give you the two pictures in the upper panels. So this is to give you an idea of, and again, we need that volume in the lower left to calculate all the forces. For example, how the angular momentum of the stars and gas are obtained, going down to scales that are much smaller than the volume as a whole. Good. Okay, so here, so that's the cosmological challenge. Let me make an aside here about where NBody simulations get used in astrophysics. So when we talk N is the number of particles, bodies we're talking about. A lot of work is done on very small n. 9 is a good number, the sun and 8 planets. This is sort of one end of the regime where there's a small number of bodies. There are, but you want to follow, say, the orbit of the Earth for billions of years, say, if you want to determine whether the Earth's orbit is stable or not. And you generally need very high accuracy. You're very interested about exactly what happens to the orbit of the Earth. And you don't have to worry about close encounters between the bodies. So that's sort of one end. In the intermediate end, there's a lot of work on objects like globular clusters, so star clusters, where n, the number of stars in a cluster, is anywhere from 10 to the 4 to a million. You're also following these things for gigayears, but the interactions between the individual stars in that situation is important. Binary stars are formed in globular clusters and dissolved. In that process, that's essentially although the stars might not actually touch, that's a type of collision where the stars interact very strongly. What I'm focusing on today is this very large n limit, where an individual star or dark matter particle doesn't feel the individual effect of another dark matter particle, but interacts with the entire collection of particles. So in that sense, there are no collisions. And there's this issue. What the n you're trying to simulate in terms of stars, it's billions. In terms of dark matter particles, we're talking 10 to the 70 or so dark matter particles. There's no way I'm going to fit 10 to the 70 particles in my computer. So we have to think about, well, what are we actually simulating when the number of particles in our computer is much, much less than the actual number of, say, dark matter particles. And so what we're doing, well, so normally when you think of NBody simulations, you think of this top formula. We calculate the acceleration of a given particle by summing the Newtonian forces of all the other particles in the simulation and adding them up in a vector manner. But in the situation where we're in the large n limit, what we're actually looking at is the evolution of the distribution function. So f here is the probability of finding a particle at a particular point with a given velocity. And the equation for that probability distribution, called the phase-based distribution, is given by the collisionless Boltzmann equation shown there, which is essentially stating conservation of probability. So the partial derivative of the probability at one point is balanced by the flux of probability in configuration space. That's the second term. And also the flux of probability in velocity space. That's the third term on the left-hand side. And so so you see that's a partial differential equation with 7 independent variables, which looks very difficult, but the way we could solve it is using the method of characteristics, where we break up our probability distribution f into packets, the delta f, and the packets will follow trajectories in position and velocity space as a function of time. And if you work out the equation of motions for these packets of distribution function, you get the last two equations. The time derivative of x is the velocity. The time derivative of the velocity is minus the gradient of the potential. And if you combine those two equations, you'll get x double dot is equal to minus the gradient of the potential, which is exactly what you have at the very top, where we're talking the Newtonian potential. So we're actually using that top equation, but underneath, we're trying to solve this collisionist-Boltzmann equation. But that still means that you've got to think about a few things. In particular, we're assuming that we have these packets of F. Capital F here is the force. So the forces between two packets should not be dominated by the single packet interaction. It should be the global potential. And furthermore, this discretization of the distribution function would excite spurious solutions that we got to be wary of. And so there's a couple things you do. One is you soften the forces between individual packets to represent that these aren't individual particles, but collections of particles. And the other point is the higher the number of particles used, the better the quality of your simulation. So now, given all that, we need a high performance solver that can scale to large numbers of particles and large numbers of processors on modern parallel machines. So I'm going to talk now about ChaNGa, the code you'll be working with. And here are some of the features. I'll talk about what I mean by tree-based in a second, and I'll talk about what SPH is in a second as well. This code is very latency tolerant. It's built on the CHARM++ runtime system, which I believe you already had a talk about. It's aware if you have multiple processors sharing an address space, it can take advantage of this. And there's a load balancing, which I'll get into as a key issue in performance. And there are other, right? It's a production code, and so it has the things you need for running on a large cluster. So let me talk about the tree here, or tree-based gravity. So if you remember that that first equation I showed you, each particle should feel the gravity of every other particle. So naively, that means calculating gravity is this n-squared algorithm. So doing 1 billion particles gets very expensive. And so how do you reduce the complexity of that problem? And the way we do this is organizing the particles into a tree where the tree is based on a recursive partition of space. So if we go to, so here we have a volume, and we're going to represent the entire volume by a single node, which will be the root of our tree. That volume is divided into 4 subvolumes, 1, 2, 3, 4. And so those are the 4 children of that tree. And then each of those 4 volumes, the yellow, are divided in 4, and that's this line of rows. And perhaps we have a greater concentration of particles towards the center of this volume. So the center subvolumes get divided even further, and the very central ones get divided even further. So each point over here corresponds to one of these cells on the left. So I want to ask ourselves, suppose I want to calculate gravity on a particle in this yellow volume. And I've located this yellow volume by this circle in the tree representation. Well, we could search through all the subvolumes over here, but there are circumstances. For example, this red volume, we could approximate, this red volume is far enough away from the yellow volume that we could approximate the forces of the particles inside the red volume by a simple expansion. So we call it a multipole expansion. That is a monopole. We could represent all the mass in this volume by one particle at the center of mass. We're a little more sophisticated than that. We take several moments of the mass distribution, actually up to fourth order moments of the mass distribution, to construct what would the gravitational field look like far away from this volume. And we can evaluate that expansion at this yellow cell. And so that replaces all the particles inside that red volume with a single multipole expansion. And you can, and you basically, you go through the tree making decisions about whether the subvolume is far enough away. In this case, this red volume corresponds to this point over here. We make a decision that the size of this volume compared to the distance is small enough that the multipole expansion is valid, and we use the multipole expansion rather than traversing down to these deeper levels of the tree. And so that for this particular point, the yellow volume, instead of traversing the entire tree, we can just take the red, the nodes of the tree indicated by the red points. And by doing so, we reduce the complexity of the algorithm from n squared to approximately n log n. And let me pause there. People have questions about the algorithm. Okay. All right, so let's think about implementing it. So we've got to distribute this tree across a large number of parallel processors. The way we do this is what we call tree pieces. So in the language of CHARM++, when you listen to Nitin's talk about that, each of these tree pieces is a char, so computational object. And within the tree piece, we have a vertical slice of the tree all the way up to the root. So each tree piece has the root node and descending to a local piece of the tree. So the green here are nodes of the tree which are entirely contained within a single computational element. But as we go up, you get to nodes which are shared between two tree pieces, and those are indicated in pink. Of course, the root, for example, is shared by all the tree pieces. And then there are external, so basically indications that if you go down this path in the tree, you'll have to go to another computational element. I should point out that I've represented this as a binary tree, whereas here this is a quad tree. But turning this into a binary tree is trivial, right? You just, each dimension, you make a binary split. So there would be another node, say, that contains the top two, and another node that contains the bottom two, to insert extra tree levels. So that's the basic data structure. We have to decompose these elements. We got to decide, okay, what piece of the tree goes on which processor. And the way this is done in most large NBody codes is via what's called a space filling curve, where we map particle positions into a single number, which we'll call a key. And one way to construct a key is, let's represent our three-dimensional positions, x, y, and z, in terms of integer numbers, basically going from 0 on one side of the cube to 1 on the other side of the cube. And if we look at the binary representation of those integers, we can interleave the bits of the binary representation to make a single binary key. So in this case, the last three bits, 1, 1, and 0, are interleaved to produce an octal 6 key, binary key. And so you can do that with all the bits and turn these three numbers into a single number with the property that this binary key number, except for the placeholder bit, will basically, as it goes from 0 to 1, it will progress through the entire volume, going from the lower left-hand corner to the top right-hand corner of the cube. And so all you need to do a domain decomposition is to pick splitting points in this single dimension, the key dimension. And to get all the particles into the right domains, you just have to sort the particles based on their binary key. So pictorially, what does this look like? What I just described to you is called Moreton ordering, and this is represented by the volume on top. So the way Moreton ordering goes, in this case, start at the bottom over here, you traverse the back of the cube, you then go diagonally to the front bottom corner, along this front corner, and then another diagonal across the entire cube, and similarly up the top half of the cube. So that's sort of the largest traversal through the domain. So these diagonal cuts that Moreton ordering does is not optimal. And so a slightly better ordering that's a little more complicated to describe is called the Peano-Hilbert ordering, and that's shown in the bottom. And in this example, you'll start at the top back, you go down, come to the front, go up, go across the front to this near corner, down, back again, and up. So that, and notice that there's no diagonal traversals when you do this. You're always going to an adjacent region. And so this is the well, it's the method, default method that ChaNGa uses, and many other codes use this kind of ordering to do your, and again, to do the domain decomposition, you just have to make appropriate cuts along this space filling curve. The other issue is right, you could do domain, well, is the load balancing issue. So you're going to do your domain decomposition so that you have equal numbers of particles in each domain. Sometimes that means you have to cut at very low levels, which is not optimal for communication. If you try to cut at always at high levels, then you have the issue that each individual processor has different numbers of particles, and that makes load balancing harder. You can also do a completely different way to do domain decomposition. To perfectly balance the number of particles is do orthogonal recursive bisection, where you bisect the cube such that you have equal numbers of particles on each side of the split, then recursively do that. The issue there is, particularly with clustered particle distributions, the shape of those volumes is very non-cubical, to put it mildly. And for gravity, you really, particularly for those multipole expansions to work well, you want approximately cubical domains. And so that's not, although that's an option in ChaNGa, it's not a desired option. So you split up your particles, and there's a matter of building the tree. Again, if you're sorting on the keys, the particles are already in the order they would be if they were organized in a tree. And so building the tree is pretty straightforward. It's a matter of just determining how many particles are on each side of a tree division. You can assign a different kind of key. This is a node key where each bit tells you which side of the tree you've descended. And then you don't go down to individual particles. It's more efficient to stop when you have a small number of particles in a node. And depending on the type of processor, you have anywhere from around 8 to 64 particles, where the larger numbers of particles in a bucket allows you to take advantage of the SIMD instructions, the AVX instructions, to vectorize operations. And then from the bottom up, you construct multipole moments. So for each leaf node, you can calculate the mass moments within that node. And then you go up the tree, combining the mass moments to create the mass moments of the node above, and all the way up to the root. And this is all done if you're in the same address space. Then these nodes are merged so that every processor in an address space can use the same tree, saving considerable space, memory. And then we have to start the gravity calculation. So this is, as the tree slide tried to illustrate, you're walking the tree. For a given particle, you're trying to decide whether a given tree node can be treated as a multipole expansion or whether I have to go to the children of that node. And to work in parallel, we have many parallel objects performing a tree walk, and we divide it up into two pieces. There's you can walk your local tree, which is fairly straightforward, and you can walk your remote tree. And the problem with the remote tree is that you have to go fetch the data. And so but you're doing both, so there's this overlap. While the global work goes and fetches data, the local work can be actually doing computation. So this is how we have overlap of communication, fetching the remote data, and doing computation on the local. Now, if we have many elements per processor, we only need, if we get a piece of remote data, that remote data could be used by many of the pieces on a processor. And so there's a processor-wide software cache that actually does the fetching of the remote data, but is able to keep it around in case another tree piece needs the same piece of data. So that saves both memory and the amount of communication needed to get data from a remote processor. I said SPH way back in the beginning. There is gas dynamics to be done, particularly when we're talking about trying to understand the structure of galaxies. And so we need a way to do that. But we need to do that in situations where we can handle high Mach number, 10 or more is typical in astrophysics. We would like a Lagrangian, in particular Galilean invariant method. And the reason for this is that, right, as the galaxy forms, the galaxy is moving through the universe. We don't want that overall motion to be affecting our calculation. Within a galaxy, in the galactic disk, for example, the sound speed of the gas is a few kilometers per second, but that disk is rotating within the galaxy at hundreds of kilometers per second. So if you're using a grid code, you're going to have to be vecting material at high Mach number through your grid. So a method that actually follows the flow, the Lagrangian method, is preferable. And SPH is that kind of method. So each particle, the smooth particle, is a sample of your gas for which you're solving the Navier-Stokes equation. And this is also a natural extension of a particle method for gravity. So for gas particles, they have gravity. So that particle is in the gravity tree. And then the same tree can be used to find near neighbors to calculate the gas properties of that particle. So there's if you think back to that picture I showed of our Milky Way, of the data set, notice that there's a large number of particles concentrated in a very small fraction of the spatial computational domain. And so this gives this difficult imbalance. You want to distribute the computation across the domain, but that means you would have to distribute that very central region across many processors, which causes both a memory imbalance, but also if you distribute it across many processors, you have a large amount of communication. So that's a difficulty. If you're doing by multi-stepping, I mean not every particle needs its force calculated every time step, but there's still fixed costs for every time step, in particular the domain decomposition, the load balancing, and the tree build. So going back to this, the load distribution. So here's another data set similar to one I showed you earlier, but each point here is not a particle. It is a tree piece. So a piece of the tree, and the color is the relative computational cost for calculating gravity on that particular piece. And you notice that as well as the computation as particles being concentrated here, it costs more per particle to calculate gravity in the center of the simulation than it does towards the edge. So there's this huge load imbalance. And the way this shows up, here's this is this is a tool called projections, part of the ChaN++ system. So what we have here is percentage utilization of the entire machine. This was run on a few hundred processors, and as a function of time, showing the different components of the calculation. And color coded. The generally blue colors are gravity. The greenish colors are the gas dynamics. The red is communication. So it turns out that gas dynamics is rather computationally intensive compared to its communication. So this green here is solving the continuity equation, conservation of mass. It's doing a lot of communication, but overlapped with this is some of the actual local gravity work, is the light green. As more data comes in, we have the remote gravity work being done in the dark green. After all the gas dynamics, the continuity equations are solved, then we have this is the momentum Navier-Stokes part of gas dynamics down here. Again, more communication. And finally, this is the energy equation solved here. But the point here is the bad load imbalance. And I've tried, in this particular instance, I have equal number of particles on each processor. And you see that this is a bad idea. Some processors are taking a very long time to get their work done, and the rest of the machine is sitting idle. If we instead load balance by the actual work, this is the, first of all, notice the total time, nearly 30 seconds, reduces to less than 16 seconds, running from the start of the gravity calculation to its finish. So this is just pointing out the importance of load balancing to make efficient use of your parallel resources. And just to brag, we've done scaling with this code out to 500,000 cores. This is the on the NCSA Blue Waters machine. What's showing here, these are for 12 billion and 24 billion particle data sets, showing both the time per step and the parallel efficiency. That is what fraction of the machine you're actually using. So these techniques I talked about are able to scale very well. And so finally, I just want to sort of brag about some of the latest results we're getting out. One of the things we've been worried about scientifically lately is the presence of supermassive black holes in the centers of our galaxies. And it appears that the presence of the supermassive black hole in pretty much every galaxy, we know our own Milky Way has one, many of the galaxies locally have supermassive black holes, and they appear to be regulating the morphology and the formation of stars in galaxies. So we've run these set of simulations with ChaNGa on Blue Waters. We call them the Romulus simulations because of the black hole connection. And this is kind of a brag slide here about how we're able to follow the evolution of these black holes, for example, as they form and merge as galaxies collide. And also black holes, like the black hole in M87, which we recently imaged, those black holes cause massive outflows, and we're able to reproduce these outflows pretty much naturally from the simulation. So there's a black hole here. It is powering a it's called an active galactic nucleus, which is producing this jet-like ejection of material, and that jet is in turn influencing the morphology of the surrounding galaxy. So those are the kinds of simulations. Both we're doing the simulation both in a volume and in individual galaxy clusters. And what we're trying to understand, well, first of all, can we reproduce what is seen? The bottom panels here are simulated observations with an X-ray telescope, with the Hubble Space Telescope in the ultraviolet, and with a radio telescope. We're trying to produce these observables to explain the structure that we see in galaxy clusters. Trying to understand why some galaxies are spiral and with lots of young stars, while other galaxies are these elliptical shapes and not so many young stars and quite old. And the age of the star changes the color of the galaxy. And then just sort of hitting the kinds of things we're trying to understand. We can see the cluster gas in X-rays, and so we're trying to understand the properties of gas. We're trying to understand how galaxies change their shape. As galaxies fall into the cluster, their gas gets stripped, making these jellyfish-like galaxies. What's stopping the star formation in the center of the galaxy? And as I intimated, that has a lot to do with the central black hole. Black holes are also interesting because there's proposed gravitational wave experiments. You've probably heard of gravitational waves being detected by the merger of black holes. In the early universe, these supermassive black holes should also be merging, and we should be able to detect them with space-based gravitational wave detectors like the LISA experiment being developed now. And finally, going back to cosmology, there's still some things we don't understand about the formation of structure. In particular, the amplitude of the structure we see in the cosmic microwave background, that first image I showed, doesn't quite match up with the amplitude of the structure we see in the universe today. And trying to understand that tension is something we're working on. My feeling is that has something to do with understanding the structure of clusters and how to interpret what we see in X-rays and mapping that onto actual mass of the clusters. All right, so just that last part to summarize it. Simulating galaxy clusters and individual galaxies is hard because of this large dynamical range. We've got to resolve star formation, and yet we need to understand gravity on these hundreds of megaparsec scales. You have this concentration of computational effort in the center of your cluster, which makes parallelization and load balancing difficult. There's other physics we probably should be including, but we're working on. But the great thing is, as machines become more capable, and both in terms of the hardware and also in terms of our infrastructure, parallel infrastructure, we are now able to tackle this kind of problem. So let me thank those who have funded this research and this software development, and also let me thank you for your attention. So I can take questions now.
If you have any questions, you can just either speak or just write it in the chat. I want to ask a few questions. I mean, if in a while, one is the analysis that we are doing. Where is it where is it basically? So the one for the IC.
You mean? I'm not sure what you mean. Where?
Where, is it close galaxy, far?
So it's very right. So all right, now I get the important point. So let's go back to where. So this is. I'm not sure if this is. This is the kind of data set we have. We are studying galaxies in a statistical fashion. Okay, so I can't sort of. It is very difficult to, shall we say, run the simulation backwards. And it's sort of the nature of the nonlinear dynamics makes that very hard. And so when I'm going to say, well, I'm going to simulate the formation of the Milky Way, what I really mean is, well, I'm going to simulate the formation of a galaxy like the Milky Way. And so, so the way this kind of thing works is we simulate a very large volume containing, say, hundreds of Milky Ways, and we look at the history of the various galaxies in low resolution and say, okay, this particular galaxy has the right mass, has the right spin, and so let's look at that galaxy in higher resolution. So again, we're not simulating a particular galaxy, we're simulating a statistical representation of a galaxy.
Okay.
So, yeah, very good question. Thank you.
Okay, there's a question here. What are the main advantages of ChaNGa over other SPH codes?
So I think the main advantage, the main advantage is its scalability. So we've worked hard to be sure we overlap, and the key is overlapping the communication and computation. So, for example, as I mentioned, SPH is rather communication intensive, and we're able to overlap that with the calculation of the gravity. And that's the thing that allows us to scale to large number of processors. Pretty much, I haven't had a head-to-head comparison, but just looking at the literature, the scalability is the big advantage of ChaNGa over other SPH codes.
Okay, so the questions. I would like to thank Tom for supporting us here and for doing this lecture about ChaNGa. Of course, if you have additional questions, we can continue via Slack, our Slack channel, and I'll see you tomorrow with the Thinker HP. Okay, and thanks again, everyone, and bye-bye.
All right. Yes, thank you everybody for listening, and bye.
Yes.